All right, everybody. I'll wait another 10 seconds and we'll begin. Yeah. Okay, let me begin. So can you hear me? Can everybody hear me?
Yep.
Perfect.
Yes.
Today we're going to be talking about independent component analysis, but first, a quick recap. So we saw in the last class what we meant by correlated variables. So if two variables x and y are correlated, then at any x value of x, the y value is going to depend on x. So here in this example, I have a scatter for a set of bivariate data points. Our example was burger consumption and penguin population. And the expected penguin population when burger consumption is B1 is different from the expected penguin population when burger consumption is B2. So these are correlated variables. The expected value of y given x varies with x. If the variables are uncorrelated, then knowing x does not tell you what the average value of y is. So in this example, both had B1 and B2, the expected value of y is exactly the same. These variables are uncorrelated. And so uncorrelatedness has all of these properties. If you have two variables, x1 and x2, then the expected value of x1 is going to be something, the expected value of x2 is going to be something. But the key point is that the expected value of x2 given x1 is always going to simply be the expected value of x2. So regardless of what x1 is, the expected value of x2 is the same. Also, the expected value, as a consequence, and we can prove this, the expected value of the product of x1 and x2 is going to be the product of the expected value of x1 and the expected value of x2. So if the data are centered, meaning if their means are 0, then the expected value of x1 and the expected value of x2 are going to be 0. So all of these terms are going to be 0. Now, when we have multivariate data of this kind, I can write the whole thing in this manner. I could write x1 and x2 as a column vector. And so we can define the correlation matrix as the expected value of the outer product of the data vector and its transpose. And that's simply going to be the expected value of this matrix, where the diagonal elements are x1 squared and x2 squared, and the off-diagonal elements are x1, x2, and x2, x1. And if the two variables are uncorrelated, and if they are zero mean, then this term, the expected value of x2, x1, as we saw, is going to be 0. And so this correlation matrix is going to be a diagonal matrix. Now, this is an expectation, but this is also going to hold true of averages. So if I have this matrix big X, which consists of a large number of data vectors, then, let me use my pointer to explain what I mean by this. So X over here is going to be something like, oh, come on. I'm sorry. X over here is going to be something like x1, x2, and so on. These are all data vectors. So if I have a data vector of this kind, data matrix of this kind, then the outer product of x and x transpose is simply going to be the average of the outer products of the individual vectors in the matrix, or rather the sum of the outer products of the individual vectors in the matrix. And if the components of these vectors are uncorrelated, that means this outer product is also going to be diagonal. So that's what uncorrelatedness means. And we also saw in the last class how we could make a pair of variables that are correlated, uncorrelated. Sorry, this should have been x2, not y2 over here. So if I have x1 and x2 which have a scatter of this kind, then I can transform the data vectors in some manner. Shoot, this equation is off. This should be x1 prime, x2 prime equals trans t times x1, x2. So I can transform x1, x2 to x1 prime, x2 prime such that the scatter of x1 prime, x2 prime is axis aligned in this manner, and the expected value of x2 prime becomes independent of the value of x1 prime. This is decorrelation. And we also saw how we could do this. If big X is the matrix of correlated data vectors, then when the data vectors are correlated, then each component of this matrix, each row, is going to tell us about the trend of the other components, the other rows. And if you want to decorrelate the data, you want to transform T such that Tx, y equals Tx, is going to be a collection of vectors. And the correlation matrix, if the data are zero mean, then that's also the covariance matrix. Then the covariance matrix of the transformed data is going to be diagonal. So y times y transpose is diagonal. And this is basically what decorrelation means. And we found that when we perform principal component analysis, this transform T is going to be the transposed matrix of eigenvectors of the covariance matrix of XX transpose. So we saw how that worked out too, right? If X is the matrix of correlated data vectors, then I want some transform T such that Tx is uncorrelated, which means if y equals Tx, you want y times y transpose to be a diagonal matrix. And that means Tx times X transpose T transpose is going to be a diagonal matrix. But this inner term over here, XX transpose, is simply proportional to the covariance matrix of X. And so we saw again that the covariance matrix of X can be decomposed using eigen decomposition into some E lambda E transpose, where E are the eigenvectors of the covariance matrix, and lambda is the matrix of eigenvalues. And we know from the properties of eigen decomposition that the eigenvectors of a symmetric matrix, such as a covariance matrix, are going to be orthogonal to one another, which means that E transpose E is going to be an identity matrix. So going back here, if I let this transform T simply be the transpose of my eigenvector matrix, then you can see that T times the covariance of X times T transpose is going to be E transpose E lambda E transpose E. E transpose E is identity. This E transpose E is identity. So this whole thing is just a diagonal matrix. So in other words, when I compute the eigenvectors of the covariance matrix and transform the data with the transpose of the eigenvector matrix, that results in a bunch of uncorrelated data. But then, what does PCA do? PCA's principal component analysis is actually performing this operation. It's projecting the data X onto the eigenvectors of the covariance matrix. So this one is basically diagonalizing the covariance matrix, but the real effect of principal component analysis is to find the directions of the major and the minor axes of the data. And so the eigenvectors of the covariance matrix are going to give you the directions of the most variance. And what principal component analysis does is to find these directions, and it rotates the space so that these major and minor axes of my covariance matrix, they now become the new axis. And this rotates the data. So PCA basically, the main operation of PCA is to find the principal axes of the covariance of the scatter of the data and make them the new axes. The fact that this results in a decorrelation of the data, it's a property we use all the time, but that's incidental. What PCA itself does is just to find the directions of most variance and make those my new axes, right? So, okay, who's this? Someone here, let me mute you. Thank you. And how can we show that projecting my data onto the eigenvectors of my covariance matrix will decorrelate the data? It's very easy. If I have my data X, I can perform a singular value decomposition of X as U times S times V transpose. And we know that the eigenvectors of the covariance matrix of X are simply U, which means I can write X equals U times SV transpose. These are the eigenvectors. So I can write this as X equals U times Y, where Y is S times V transpose. And then what this is that Y is the representation of X in terms of the columns of U. And if you work this out, but then Y times Y transpose is going to be S times V transpose times V times S transpose. But V transpose V is an identity matrix. So this simply becomes S times S transpose. This is a diagonal matrix. In other words, when I perform PCA, I'm representing my data in terms of the bases in U. And Y are the new coordinates. But the new coordinates have this property that they're uncorrelated. So the uncorrelatedness that results from PCA is an incidental property of projecting the data onto the eigenvectors of the covariance matrix. Now, that sounds like a lot of gobbledygook, but the key point over here was that when we perform PCA to orthogonalize the data, to orthogonalize the covariance matrix, what we are really doing is finding the eigenvectors of the covariance matrix and projecting the data on the eigenvectors of the covariance matrix. And this has the consequence of making the data, the components uncorrelated in the new representation. So that was uncorrelatedness. The other statistical characteristic we discussed in the last class was independence. If you have two variables X and Y, they are dependent if knowing X gives you any information about Y. And X and Y are independent if knowing X tells you nothing at all about Y. So that has this characteristic statistically. Two random variables X and Y are independent if the joint probability of X and Y is simply the probability of X times the probability of Y. And if this holds, then this also means that the average value of X is the same regardless of the value of Y, because X doesn't inform about Y. And so independence implies uncorrelatedness, but the reverse is not true. We also saw this in the last class. So before I continue, let me just give you a poll. And let's see if we can. Can you guys see the polls?
Yep, we can see the polls.
Okay, 10 seconds, guys. Right, let me end the poll. So what do you guys think the answer is? What is the answer to the first question? The objective of PCA is to decorrelate the data. Is that true or false? True or false, guys? It's actually false. Decorrelation is an incidental outcome. The objective of PCA was to project the data onto the principal axis. You want to convert the principal axis of the scatter to the new axis. This has the consequence of making the representation uncorrelatedness. Why this matters, we will see this in a few minutes. Also, for the second one, which is the correct answer? Do you want to tell me?
The second one is the correct
Second.
answer.
Yeah, because if x and y are independent, then the expected value of x squared y squared is going to be the expected value of x squared times the expected value of y squared, right? So let me stop sharing this and kill this poll. Let me continue. Now let's talk about finding bases. What was all of this? What was all of this about? Go back to the music example. If I, in one example, we saw how given notes we could find the score. We also saw how given the score we could find the notes. But then when we want to find the building blocks of the music itself, you want to find both the notes and the score. So you want to find both the W and the H. So you want to find the bases W that best explain the data in a meaningful way. That was what we wanted to do, right? But then what do we mean by meaningful? The first attempt, let's say these bases must be orthogonal. And if you want the bases to be orthogonal, that means that you're approximating m as w times h. You want to minimize this approximation error. At the same time, you want to make sure that the bases are orthogonal, which means w transpose w is an identity matrix. So I add this Lagrangian. And when I solve for this, you just end up with PCA. So now you're going to find that these guys are the eigenvectors of the correlation matrix of M, covariance matrix of M. And these are how you would modulate these bases to compose the music. So M equals WH would be your approximation if you didn't use all of your bases. But then in the process, what happens is that because of the property of PCA, because these guys are your principal axes, H ends up being uncorrelated, as we saw. And so when we perform PCA, you're decomposing M equals W times H. The orthogonal columns of W are the bases that you have learned. And so the columns of W are going to represent the notes that we have sort of derived from the music. Now, the rows of H are their corresponding modulations, as we remember from the linear algebra class. So the contribution of the ith basis to the music is going to be Wi, the ith column of W, times Hi, which is the ith row of H. And so how does that look? Here is the original music again. If I can play this. Is this playing?
No.
No,
Okay.
we can't hear it.
So I think I've got to share this again with the music, with the sound. Let me give me a second. There's okay. Let me stop the share and share sound. So can you hear this now?
Yep.
Sorry, I'm messing around. Okay. And shoot. This is terrible. Oh my God, what just happened? So bear with me. Zoom is a bit of a problem. So here we are back again, right? So if I use PCA to decompose this was the music. There are 12 notes on the segment. And please don't do this. If I decompose it using PCA, then these are the bases that I have learned. Each of them, along with each of these species, you've learned its own modulation. And what is the first component that we learned sound like? It doesn't really sound like a note. It's like some odd combination, right? That's what we found for each of these guys. There's the second one. Each of the so-called 12 notes that we find don't really sound like notes. The results are not good. So, come on, please. Pardon me, my tablet is misbehaving badly. This is not going to work today. Guys, if this fails, I'll cancel the class and redo it because this is equipment failure.
Is it doing it automatically?
Yeah.
Maybe you can unplug your tablet and just use your
No, so
computer.
this is my mouse misbehaving. Sorry.
Remove the mouse and use the touchpad. Maybe that may fix it.
So, but then if I remove the mouse and use the touchpad, I can't play any of the stuff. So let me try this again. Every time I touch my mouse, the thing flies off.
Instead of using your mouse, you can try using your touchpad for playing the noise also.
No, but then this is my tablet. It doesn't, it's a detachable screen.
I see.
Right? So I suspect this class will run over. Please bear with me. This is issues. So here's where we were, right? We found that the notes we learned were useless, right? Oh, come on. Guys, I don't think I'm going to be able to do this class. So I apologize. I'm going to try to do this on this. Let me redo this, reshare this with my desktop and I was hoping to write stuff, but that's not going to happen. Let me try this.
Prof, do you have a computer with you?
I have exactly. That's exactly what I'm showing this on, right?
So
So
can we try sharing the screen from the computer and trying it
what I'm
out?
going to be doing. That is what I'm
Okay.
going to be.
Got you. Go.
All right. And okay, my sincere apologies. I'm going to be using the same mouse on this guy. I hope things don't run, but can you see my screen?
Yes, Prof.
Okay. So here's where we were, right? We found that the notes were not really working very well. So why was that? The reason is PCA decorrelates the data kind of incidentally. If this is the scatter of the data, then these are the principal axes of the data. And when you perform PCA, these principal axes become the new axes. PCA always makes the principal axes of the data the new axes. And decorrelation is a consequence. But then, can you see any other axes over here that would also decorrelate the data? Can anybody see them? Over here? Anyone? So
Shifted by 90.
Completely diagonal, like 45-degree.
right. So yes, basically, if you had these two axes, you have other axes which decorrelate the data. So here's what we can do. Let me try to focus on decorrelating the nodes rather than just saying that my nodes are going to be the principal axes of my scatter. If I want to decorrelate the nodes, what this means is that if you look at the score matrix, you want the correlation matrix of the score matrix to be diagonal, which means H times H transpose must be diagonal. We're not specifying what D is. We're just saying H times H transpose must be a diagonal. If I use that as my constraint, my new optimization is going to be trying to find W and H such that the squared norm is minimized while ensuring that the correlation matrix is diagonal of the score is diagonal. Is this making sense? This one here?
Yes.
Okay. And when that happens, you know, what are the bases that will give us uncorrelated correlation matrices? We already know one, which was our the eigenvectors of the covariance matrix. But then here, these guys, these axes also would decorrelate the data. If I made these axes the new axis, the scatter of the data is going to be such that the data are that the components are uncorrelated. Nonetheless, PCA is not going to find these axes. PCA is always going to find these axes. Why is that? Can anyone tell me?
PCA finds the axes that best minimize the amount of like lost information, and they'll always be the same.
Exactly. So PCA is always going to try to find the directions that minimize the lost information. And those are going to be the principal axes of the scatter of your data. PCA is not going to find other decorrelating axes. Right? So if you have a different technique, which is based only on decorrelation, which says, I just want to find bases such that the scores are decorrelated, it could find either of them. In fact, there are many, many axes which would decorrelate the data in this particular case. And the decorrelation-based technique can find any of them. So there's a difference between a decorrelation-based technique and principal component analysis. PCA is going to find the principal axes. Decorrelation is incidental. A purely decorrelation-based technique could find any of the axes that decorrelate the data. That makes sense?
Yep.
Right. So I think things will go smoothly from here. So what's special about these blue axes and how can we modify the decomposition to find them? That's what we're going to look at. Here's another example. I have this scatter. If I perform principal component analysis, it's going to find the major axes of the scatter. They are going to become the new axes. And when that happens, the resulting scatter is going to be uncorrelated, meaning the average of X is going to be always the same for every value of Y and vice versa. But do you see any other axes that would decorrelate the data over here? Anybody? Do you see any other axes? These guys, right? These axes, if I make them my new X and Y axes, this is going to be the new scatter. And in the new scatter, you can see once again that X and Y components are decorrelated. In this case, why would PCA not find these axes? Can anybody tell me?
Because they don't explain the data the most.
They don't explain the scatter, but they are also not orthogonal to one another. And PCA will only find bases that are orthogonal to one another, right? Because PCA is going to find the eigenvectors of the covariance of the correlation matrix, which happens to be a symmetric matrix, and the eigenvectors of a symmetric matrix are always orthogonal. So PCA will fail here as well. It's going to find only this guy. So again, what is special about the blue axes? And how do we modify our decomposition to find these blue axes instead? So we're obviously just decorrelation is not enough. Simple decorrelation, PCA is not enough, and simple decorrelation will decorrelate stuff, but then it's going to give you a non-unique answer. So what else can we look for? I can assume that the transcription of one note does not depend on what the rest of the notes are playing. That is, in a multi-instrument piece, the instruments are playing independently of one another. Now, this is not strictly true, but I can make this assumption. And so if I do that, I can now use that as a constraint and try to find statistically independent components of the mixed signal. This is independent component analysis. So here, I'm going to say that the rows of my score matrix are statistically independent of one another. And this is the new Lagrangian that I would want to impose, except of course, this is not nicely specifiable in a functional form. So we're going to have to go about this in a roundabout way. And if we manage to do that, here's what we find. If I make these axes my new axis, not only are the x and y components uncorrelated, what you find is that the distribution of y, the entire distribution of y, not just the expected value, is the same at every value of x. And similarly, the distribution of x is the same at every value of y. If we find these axes, then the resulting coordinates, the resulting components are statistically independent. And so this is independent component analysis. ICA searches through all possible combinations of bases to find the set of bases that makes the representation of the data in terms of these bases maximally statistically independent. Does that make sense?
Yep.
Right. What about the rest of you guys? Did that make sense? Right.
Yep.
Okay, I got 2 yeses. So
Yeah.
let me see if I can pull up this poll and release poll 2. Can you see this poll?
Yes, Prof.
I'm not going to give you the full minute because I wasted a lot of time with my stupid mouse. So 5 seconds. All right. What do you guys think the answers are? For the first statement, if there are multiple decorrelating axes, the solution to PCA will be indeterminate. True or false?
False.
False.
It's always going to find the scatter, maximum scatter, right? And ICA, true or false?
True.
True.
Perfect. And so that's what we find, false and true, okay? So I'm going to change the problem setting for a bit because we're talking about ICA, because this is the common setting in which ICA is discussed. Let's say I have 2 people speaking, speaker 1 and speaker 2, H1 and H2. I'm capturing the data using 2 different microphones. So the distance between from speaker 1 to mic 1 is different from the distance of speaker 1 to mic 2. So also the distance of speaker 2 to mic 1 is different from the distance of the speaker 2 to mic 2. So what happens is, because the gain value depends on the distance, mic 1 is going to capture some W11 times H1 plus W12 times H2. Mic 2 is going to capture some other W21 times H1 plus W22 times H2. So the gains of this speaker to this mic and this mic are different. So also the gain of this speaker to this mic and this mic are different. But what happens is that each of the mics is going to capture a different mixture of both signals. So if I were to write the whole thing out in symbols, if these are my 2 signals and these are the signals that are captured by the 2 microphones as represented by this matrix M, and if these are the signals actually produced from the mouths of the 2 speakers, then the first signal captured is going to be W11 times S1 plus W12 times S2, or this H2. And the second signal is going to be W21 times H1 plus W22 times H2. And so the actual recorded signal can be written as M equals W times H. Is this making sense?
Yep.
Right. So, Izera, what was the question? What does it mean to have orthogonal ICA components? I'm not sure where that term came up, but we'll go through ICA and we'll see that. So again, later. So here is the signal. Here are the signals recorded by the microphones. And what really happened was you had signals generated by the speakers. They were mixed by the so-called mixing matrix. And so you ended up with this mixed signal, which was the signal recorded by the microphones. And now our problem is going to be all over the same. It's going to be the same again, given only the mixed signals. I want to extract the signals generated by the individual speakers, which is the same problem as before. You're given this mixed signal M, and we want to find W and H such that W and H combine to give us the mixed signal with one additional characterization. You want the rows of H to be statistically independent, because what speaker 1 says, the signal produced by speaker 1 has no immediate dependence on the signal produced by speaker 2. So here's an example of mixing. This one, let's say I had two sinusoids, the pink and the blue, and I could mix them using some mixing matrix as we just saw. The result is going to be this. One mixed signal is going to be the blue curve here. The other one is going to be the orange curve here. And our problem is to try to recover this signal from the mixed signal. We want to recover both the signal here and the mixing matrix, because all you will have after you're done recording is the mixed signal. So is this problem making sense to you? What about the rest of you guys? It's making sense? Okay. So here again, we have the mixed signal M. We want to decompose it into W times H, except that we know that the rows of H are statistically independent. Now, it's obvious, right? H I can simply write as W inverse times M. If I write W inverse as A, then I can write as H as A times M. So W is your mixing matrix, which mixed H down to M. A is your unmixing matrix, which unmixed M back to H. This terminology making sense?
Yep.
Okay. So this is the form we have, right? H equals A times M. And so we want to recover H from M. Now, how do you recover H from M? One simple way was to try to decorrelate M. That's what PCA did, what the decorrelation-based techniques did. But that didn't actually recover H, because we saw that that gives you something like, in the case of the music, we didn't actually recover the independent notes. So also over here, simply decorrelating stuff will not work. Instead, we want to find some other linear transform A, such that when this linear transform A is applied on M, the result is going to be an H matrix where the rows of H are statistically independent. So our search is for this matrix A, which results in statistically independent rows in H. So we decorrelated the rows of H by diagonalizing the covariance matrix through eigen decomposition. Our question is there a simple matrix we could just similarly diagonalize to make them independent? Some matrix whose eigenvector matrix gives us the transform A such that the rows of AM are statistically independent. Are these statements making sense?
Yes, they are.
Right. So we're trying to do something very similar to decorrelation, except we want independence. So if I have a scatter of this kind, PCA would simply find these two red axes. That's not what we want. Instead, we want to find the axes. So we want to find the transform of this data such that after transformation, it looks like this, so that the two axes are statistically independent. And so here's what happens. If you mix these data, if you start off with statistically independent data, after you mix it, assuming there's no scaling, mixing is basically a rotation. Independent component analysis is going to try to unrotate the data. Unfortunately, this cannot be done for Gaussian data. Why can this not be done for Gaussian data? It's very easy to see. Let's say my original data were Gaussian, then the scatter is going to be a perfect circle. It doesn't have any kind of a shape of this kind. So mixing is going to rotate the circle. Now over here, what we wanted is, if the distribution was a square, rotation would give us something that was a parallelogram, which is rotated, right? And then unmixing would try to somehow find a transform which would rotate this back into a square. But then if the original scatter itself is symmetric and circular, then rotating it is also going to give you a symmetric and circular rotation, scatter. And there's no way of finding out how to unrotate it so that it comes back to this original scatter, because there's no shape available. The distributions are perfectly symmetric. And so independent component analysis will not work for Gaussian data. That makes sense?
Yep.
What about the rest of you guys? Did that make sense? So ICA doesn't work for Gaussian data. Keep that in mind. So here's our problem again. Is there a linear transform that can transform this scatter into something like this? Now, again, I keep flipping between correlation and covariance because I'm going to assume that the data are zero mean. We are saying M equals WH. This recorded data are some mixed version of H. We want to unmix stuff. But then if the mean of M is 0, then it immediately means that the mean of H is also 0, because M equals W times H. So if the mean of M is 0, then the mean of A times M is also going to be 0, so the mean of H is 0. So also if the mean of H is 0, then the mean of W times H is going to be 0, so the mean of M is also going to be 0. Keeping this property in mind, what I can do is to simply find the mean of the columns of M and subtract it from every column. And that's going to give me a new matrix with zero mean. So anytime I have data which are non-zero mean, I can always center them by subtracting the mean out. And so I can just assume that all my data are zero mean. So that's where we're going to begin. We're going to assume that all data are zero mean to begin with, that the scatter is always centered at the origin. And now our problem is to find out the transform that will convert this data to a square, right? The scattered over here to be a square, which makes the components independent. But as a first step, we are going to decorrelate the data. Why decorrelate the data? We know that if the components are independent, then they are also uncorrelated. So we will ensure that they are uncorrelated to begin with, which means I'm first going to try to rotate the scatter in this manner so that the main axes become the new axes. But then I'll also rescale it so that the variance along each component is identical, so that the data now have identical variances along each axis. So this process is called whitening. Is this picture making sense?
Yes.
Right. So this is what I'm going to do. And how would I do this? So anyway, so why do I want to do this? The first step, I'm going to decorrelate my data, which will give me this scatter. Now I can work on this matrix, this scatter, and try to figure out how to rotate it so that that scatter becomes this. So there's an initial decorrelation step. And once things become equal variance in every direction, then I can find out the rotation that's going to make it independent. That's what our process is going to be. Does this make sense? This sequence.
Question. For decorrelating it, do we just use something like PCA?
That's exactly what we're going to do. For decorrelating it, we want to make the principal axis the new axis. But if you make the principal axis the new axis, the scatter or the variance along the different components are still going to be different. So you will normalize to make the variance along the different components the same, which means that, if this M is my original data, I can find its covariance matrix I can perform an eigen decomposition, which gives me E lambda E transpose. So lambda, the diagonal elements of lambda give me the scatter along each of the components. So if I scale each component by the inverse square root of the variances, then that's going to normalize the variance along each direction. The variance in each direction now ends up being 1. And so the matrix that converts this scatter to this guy is going to be lambda raised to minus half times E transpose. Did this make sense?
Yep.
What about the rest of you? That makes sense? Right. And so this is whitened because now if you look at the transform data, CM, and compute its covariance matrix, you'll just find it to be an identity matrix. So this matrix C is the whitening matrix, and we know how to compute it. This is just straight up PCA. So for now, I can assume that it's whitened. I'm going to begin working with X. So I have X equals CM, X is whitened. I know that the XX transpose must be is an identity matrix because X has been whitened, right? But then I want to find a matrix B such that the rows of B times X are independent. Basically, if this is the case, B's got to be, again, going back to this picture over here, right? What am I doing to the scatter? Am I transforming it in any odd way, or am I rotating it? What am I doing?
Rotating?
Rotating, right? Can you see what I'm doing here, guys? Once I get it this way, what I'm doing to make all the components independent is rotation. Is that apparent?
Yes.
Yes.
The rest of you guys, right? So basically that means that this matrix B over here must be a unitary matrix. Unitary matrices are basically just rotation matrices. So we want to impose this constraint that B times B transpose equals B transpose B equals identity matrix. You know that the transpose of the inverse of a rotation matrix is its own transpose, right? And so you want B to be a unitary matrix. You want this property for B. This makes sense?
Yes.
Yes.
The rest of you guys, does it make sense? Okay,
Yes.
easy, right? So here is where we are again. You decorrelated the signals by diagonalizing the covariance matrix. We want a simple matrix that could simply that we could obtain through some diagonalization that could now be applied on the data to make the components independent. It just turns out that there's no such simple matrix, right? There's no simple way of finding a rotation that will make the components independent. It's too complicated. But then we can try to make it somewhat independent. There's a matrix that you can diagonalize using something very similar to PCA, which will make the fourth order moments of the distributions of the two components independent. Decorrelation made the second order moments independent, right? The expected value of x1, x2 was 0. So there's some other matrix which you can use, which will do this. If you transform the data with this, then if you take the expected value of HI, HJ, HK, HL, this is simply going to be end up being the expected value of the product of the expected value of HI, HJ, HK, and HL. Similarly, if you remember, see that there are 4 components here. If you get the expected value of HI squared, HJ, HK, so their total power is 4. This is simply going to be the expected value of HI squared times the expected value of HJ times the expected value of HK. So also the expected value of HI squared, HJ squared is going to become the expected value of HI squared times the expected value of HJ squared. So this is making the fourth order moments independent. Do you understand what I mean by making the fourth order moments independent? Over here. Yes, no?
Yes.
Yes.
Right. Basically, if I take any term which multiplies 4 terms, and I take its expectation, that's going to decompose into the expectations of the individual components. And there are many different ways of coming up with a product of 4 values. Here, all 4 values are different, which means the expectation of the product of 4 values is going to be the product of the expectation of the 4 values. Here, one term is squared and the other 2 are different. So you end up with E of H1 square, Hi squared plus times expected value of Hj times expected value of Hk, and so on. So these are all the various 4th order moments, and they can be made independent. So this is what we're going to try to do. Here's what I do. The 4th order moments of H have the form Hi times Hj times Hk times Hl, right? So if the rows of my big matrix H were independent, then this is the property I would find, correct? So I want to find a matrix B such that if I multiply my whitened data X with B, then the rows of H are going to have this property. This making sense?
Yep.
This is called the 4th order blind identification, or 4B algorithm. And so here's how it's going to work. I'm going to create a matrix of 4th moment terms that I can diagonalize. Now, remember, H is a bunch of rows. This is, let me call the kth column of this HK, okay? So here is one 4th order moment matrix, which is, if each column were called H, then I can multiply H by H transpose. This is squared. And then I can scale the whole thing by the squared norm of H. So if I take this expectation, the empirical term, the empirical equivalent for this is simply the sum or the average over all the columns of H of this guy here, where for each column, I'm multiplying the column by its own transpose, but also multiplying it by the squared norm of the column. And can you see that this is actually a 4th order term?
Yes.
There are 4 powers, right? H squared times H times H. So the power is 4, right? So this is a 4th order moment matrix, correct? I got 2 ASs. What about the rest of you guys? Do you see that? This is a 4th order moment matrix.
I have a quick question.
Yeah.
Why do we specifically use 4th moment?
In
term?
principle, you want to use all infinite moments. It's just
Uh-huh.
impossible. So what we are decorrelation freed up the 2nd moment, correct?
Yeah.
So the next step we are going to make the 4th moment independent. This doesn't mean that the variables are fully independent, but they are independent until the 4th moment.
Gotcha. All right, thank you.
Right? That's what we're going to do. And so how do you compute it? So if these are my H's, then I can define this matrix D, which is the expected value of norm of H squared times H transpose, which is and so the ijth element of D is simply going to be the sum of the squared elements. So this is the average over all the columns of the matrix H. And for each column, you are summing all the squared components within the column, and you're multiplying it by the ith component and the jth component. So this is Hi times Hj, whole thing multiplied by the squared norm of the vector. This is what you're averaging. So how is this different from your correlation matrix? Can you tell me? How is this different from the correlation matrix? Anybody? Abhishek?
No, not sure.
Can someone tell me how this is different from the correlation matrix? What extra term does it have?
The HK squared norm term is different.
The squared norm is an additional term, right? If you didn't have the squared norm term, you just have H times H transpose. That's a 2nd moment. If I multiply that by this extra term, now this becomes a 4th moment, correct? Everybody see that? Right. What about the rest of you guys? You see this? And computing this is not hard. This is very trivial, is it not? This is like one line of code, right? And so that's your D matrix. You're taking the outer product of these H's, but then you're also scaling it by the squared norm and then taking the average. That's your D matrix. And so let's see how this D matrix is. The entries of D matrix are going to have this form, right? Each entry is going to be the expected value of HI. The ith component of HI is the ith component. Hj is the jth component, right? So the entries of this D matrix is going to be the expected value of Hi times Hj times the sum of the squared components, all the square of all of the components, right? You see this? You see this over here?
Yep.
Now, we know that this one includes Hi squared. It also includes Hj squared, right? Because this is the sum of the square of all of the components. So I can write this as expected value. If the H's were independent, then this is going to be the expected value of Hi cubed, expected value of Hj, plus the expected value of Hi times the expected value of Hj cubed, right? Plus the expected value of Hi times the expected value of Hj, and because all the components are independent, plus the sum over all components that are not I and j of the expected value of the squared component. You see this? Can you see how this is true?
Yes.
So this is going to be if I is not equal to j, okay? And because the data are zero mean, each of these expectation terms is zero. So for I is not equal to j, this is going to become zero, right? You see that?
Yep.
Right. Whereas if I equals j, then there's going to be a fourth power. And the expected value of a fourth power is the expected value of a positive term always. That's not going to be zero. Correct? Do you see this one?
Yeah.
What about the rest of you guys? Do you see that?
Yep.
Right. So if I define my D matrix for H in this manner, then we know that if the rows of H are statistically independent, then this D matrix is going to be diagonal, correct?
Yes.
Everybody see that? Give me a yes or no. Right. So Abhishek is saying, will it matter what H is we use? It won't matter, right? So long as I is not equal j, this is not going to matter, right? Will it, Abhishek?
Oh, got it. Got it. I think the
Right.
final step here. Yep.
So basically, now again, we have X, which is our whitened data. We want to find some matrix B such that H equals Bx. And we want this D matrix to be diagonal for H, right? But then if I look at the fourth moment of matrix of H, it's the expected value of the squared norm of H, which is H transpose H, times the outer product of H, which is HH transpose, right? You see this equation to the left? That's the same as this guy here. This one here, right? Do you see that?
Yes.
That this, right? And so I can write this out. I can write H equals Bx. So for individual columns of H, there's a corresponding column X. And so H equals B times that column. So if I write it out, this is going to be X transpose B transpose B times X. That's what I got here. Plus B times Bx, which is H, times X transpose B transpose. So do you see this?
Yep.
Yeah. But then we said B is unitary, correct? So if B is unitary, B transpose B is an identity matrix, right? So can the rest of you see this?
Yes.
And so now I can just write this out as expected value of X transpose X times BX times X transpose B transpose. But what is X transpose X? This is a scalar, correct?
Yep.
So I can bring the B out. And so you want B times the expected value of X transpose X, XX transpose times B transpose. You want this guy to be diagonal, right? Do you see that?
Yep.
What about the rest of you guys? Do you see that this you need this to be diagonal? Not everybody's seeing that. Did I lose anyone here? And so now I can write this as, again, X is my white-end data, right? I want to find a matrix B such that B times this matrix times B transpose is a diagonal matrix, correct?
Correct.
Can you tell me how I would do that? Anyone? How could I do this? I can decompose, correct? I can compose this matrix. This I know how to compose. I've got the x's. So I can compute this matrix E, which is simply the average of normed x squared times xx transpose, right? And then I can eigen decompose this D matrix as U lambda H U transpose. And then I can just set B to be equivalent to U transpose. And if I do this, then this matrix becomes diagonal, right? Do you see this, guys? Right. What about the rest of you? And so here is the simple thing. D is this matrix dx was just this expected value of normed x squared times xx transpose. I eigen decomposed it. I took the eigenvalues and used its transpose and called my matrix B this guy. You know that the eigenvalues or eigenvectors of D are going to be a unitary matrix because they're all orthogonal vectors. And so if I compute H equals Bx, which is U transpose X, then it's very easy for you to check that the fourth moment matrix of H is diagonal, which is what it would be if the rows of H were statistically independent. And so here we got this algorithm. Our overall objective was to estimate some matrix A such that the rows of H equals AM are independent. So the first thing we did was to whiten our data M by computing the covariance matrix of M and its eigenvectors and eigenvalues. And you computed your whitening matrix C, and then, which is lambda raised to minus half times E transpose. And then you multiplied the original data M by this whitening matrix to get the whitened data X. And then for this, we subsequently on X, we computed the fourth order matrix, which was this guy, and computed its eigenvectors, and the transpose of the matrix of eigenvectors of this fourth order matrix of X is going to be the final rotation, which makes all of the components independent. So the matrix that actually makes M, the rows of M statistically independent, is going to be the product of B and C, because C first whitened M, and then B rotated it to make it independent. So if you go back to this picture here, way back, C was the matrix which made this guy this, and B was the matrix which made this guy further to this. And so the matrix which makes this data over here, like so, is the product of B and C. That makes sense?
Yep.
Right? And so that was easy. You know, it looks like a lot of ugly math, but then if you work your way through, this actually turns out to be fairly simple, does a decent job, and this is the Phobie algorithm. Now, the Phobie algorithm only considers a subset of the fourth order moments. So there's a better version of this called JADE by J.F. Cardoso, which is joint approximate diagonalization of eigenmatrices, which frees up more of the fourth order cumulant matrices. But both of these are kind of approximating statistical independence. Now, why am I calling it approximating statistical independence? Can anybody tell me? Why is it approximating statistical independence?
Does statistical independence require like the infinite number of moments to all be
Exactly, right. So if the rows of H are statistically independent, the second moment matrix would be diagonal, the fourth moment matrix would be diagonal, but the sixth moment matrix would also be diagonal, and the eighth moment matrix would also be diagonal, and so on, right? Here, we just made the second and fourth order moment matrices diagonal. So it's kind of decorrelation only made the second order moment matrix diagonal. Phobie and Jade make both the second and the fourth order matrix moment matrices diagonal. That makes sense? Questions, guys? Did that make sense? Right. So it's kind of approximating approximating independence. Now let's see if I can set up the third pole. What's going back? Something is off. Shoot. I'm not able to pull up the third pole. So maybe we can just answer this question. Which of the following statements are true of Phobie? It computes a transform that makes all fourth order moments independent. Is this true or false?
False.
It requires the first pre-whitening step.
True.
The transform is the eigenvector matrix of the fourth order moment matrix.
False.
True. The transform is the product of the eigenvector matrix of the fourth order moment matrix of the whitened data and the whitening matrix.
That's true, right?
True.
Yeah, so only the first, second, and the fourth are true, right? So this is one simple way of trying to make data components independent. But then that's only making it somewhat independent. So let's try something different. Let's try using the statistical properties of mixing. The central limit theorem says that the sum of independent random variables will tend towards a Gaussian distribution, even if the independent random variables don't have a Gaussian distribution. Why is this the case? So here is something that you're going to have to believe me. For a given variance, the Gaussian distribution is the most random distribution. It has the highest entropy, right? So anytime I add two noisy random variables, it's like adding noise to an already noisy variable, correct? So you're going to increase the randomness. Do you agree? Right. If I take some noise and add more noise to it, it's going to become noisier, right?
Yeah.
Right. If I take one random variable and add another random variable to it, it's going to become more random, correct?
Correct.
So if I keep adding more and more random variables, in the limit, it's going to be as random as it can possibly be. It can't be any more random. And which is the distribution that represents this distribution, which cannot be any more random? That's the Gaussian distribution. because the Gaussian is the most random distribution. That makes sense?
Yep.
Right. So it's easy to prove that if you just show that the Gaussian is the distribution with the highest entropy for a given variance, then you can show that the distance to this Gaussian keeps decreasing as you keep adding more and more variables. And so anytime you sum independent random variables, the sum will always be more Gaussian than the component signals. You agree?
Yes.
Right. Which is why if you add two Gaussian random variables, you're not going to make it more random. They're already maximally random, which is why you cannot perform independent component analysis on random variables that are already Gaussian. So again, going back to this problem, right? Let's see how we can, I'm going to change notations for a bit and see how we can achieve the same kind of property using this notion of Gaussianity. Okay. So here was our data. So I've changed symbols. S was the signals. X was our recorded data now, just simply because my slides are mixed up. So your mixed data, X equals A times S, where A is the mixing matrix, right? And I want to find an unmixing matrix W. Sorry for switching the symbols. I didn't have time to fix my slides. So I want to find an unmixed mixing matrix W such that W transpose X gives me independent components Y that are almost the same as S. So did the change of notation make sense over here?
Yes.
Okay, just bear with me, right? So then each component of Y is going to be one row of W times X, where X is the mixed data, right? So, or one row of W transpose. So W is going to be one column of big W, okay? So here, if Y equals W transpose X, which is basically saying that, let me try to see if I can use a pen. I have Y where the components, so this is Y, right? This is going to be this is my unmixing matrix W transpose times my mixed signal data, which is going to be a bunch of vectors. Now, really, although I'm drawing vectors, what I mean is that the rows of this guy are statistically independent, right? Whereas the rows of this guy are mixed up. So if I consider any particular row over here, that's going to be, if I consider any particular column over here, that's going to be, what am I talking about? If I look at any particular element of this column, that's going to be one row of W transpose times the corresponding column X. So this X represents this one vector. This small y represents this one component. And this W transpose represents this one row. Did that make sense in spite of the confusion? Right. Rest of you guys, that makes sense? So X was the mixed matrix, right? X was AS. And so S equals A inverse times X. This is what we have. And Y was our unmixed data, which we got from unmixing X. Any single component of Y is W transpose X, as we saw. So I'm going to define a convenient variable Z, where Z is going to be the transpose of the mixing matrix times this column of W. And so when I write Y equals W transpose X, I can write Y equals W transpose AS, because X was the mixed S, which I can write this as W transpose A times S, which I can write as Z transpose S. This makes sense? This is just manipulation. This equation over here. Right. And so Y is I want y to be picking one of the s's, basically, right? So what does this mean? Y is a linear combination of these sources. If I wanted to pick only one of the sources, then I want z to be a one-hot vector. Basically, I'm saying I want my unmixed data to pick one of my component segments, which means I'm multiplying this column vectors of S, which is a vector of sources, by a one-hot vector, which picks up one of the sources. Does this make sense? Right, this is basically a selector, correct? And so these are my sources. If I multiply it by Z transpose, I'm just going to be picking up, say, if Z is 0, 0, 1, I'm picking up S3, right? What does this do for us? Since the sources are independent RVs, any mixed Y is more Gaussian than any of the sources. So here's the thing. If I check for the Gaussian of Y, correct? If I take any vector Z and multiply it by S, so long as, the components of Z sum to 1, right? Unless this thing is going to be least Gaussian when Z is one-hot. Can you see that? Yes? Because if Z is not one-hot, then I'm getting some mixture of sources. And we know that when we mix sources, it's going to be, you're going to increase the Gaussianity because you're increasing the randomness, right? And so only when Z is one-hot that you're picking only one sources, and that's when this is going to be least Gaussian. That makes sense to all of you?
Yep.
Okay, so if Y is one of the sources, it's least Gaussian. And so this is, we are not given S, right? Z is a variable we defined for convenience. So what we are going to do is to just using the same principle, I'm going to find my vector W that minimizes the Gaussianity of Y. And that should give me an independent component. That makes sense?
Yep.
Right. And this is based on statistical properties. There are a couple of different techniques for this. We are out of time. The first technique is based on, we use something called contrast functions. How do you define the Gaussianity of Y, right? I want to find the Y that's least Gaussian. So one way to do it, they check the kurtosis of Y, and then they maximize the kurtosis of Y to make it most Gaussian. But that's it. That it turns out doesn't work very well. So instead, what we are going to do is look at something called negentropy. Now, we all know what entropy is. This is the entropy, right? It's a minimal number of bits sent for an optimal code. It's a measure of surprise. A random variable that's more random will always have larger entropy. And a random variable that's less random will always have smaller entropy, right? And so the entropy of a Gaussian random variable is going to be maximum because that's the most random. So the entropy of a Gaussian is the largest possible value of any distribution with the same variance. I just said this. That's why it's the most random variable. How does this help us? I can define this function. So let's say I have x. I can and x has a variance, x has an entropy. Now, if I had a Gaussian with the same variance as x, that's going to have some entropy. This difference, the difference between the entropy of a Gaussian with the same variance as x and the entropy of x itself, right? When is that going to be maximum? When x is least Gaussian, right? This makes sense? So this is a contrast function. This is what we call negentropy. And we're going to try to maximize negentropy. So here are some examples, negentropy. If here are two random variables with the same variance. This is a If the data are Gaussian, you find that this negentropy is 0. On the other hand, if the data are Laplacian, you find that the negentropy is 1.07. So, and if you just do this using samples rather than the actual distributions, if I draw samples from it, you'll find that the negentropy is 0.08, whereas the negentropy for the Laplacian is 0.717. So drawing samples and computing the negentropy is actually an effective thing to be doing. So negentropy is a very well justified measure of Gaussianity. It's in fact an optimal measure of Gaussianity, but it's computationally hard to compute. And this means you want to estimate the PDF for random variable, which is really horrible to do. So typically you approximate negentropy and maximize over that. And so there have been many techniques for this. Fast ICA is one. Given any x, you want to maximize the difference between the entropy of a Gaussian with the same variance as x and the entropy of x itself. So x is going to be my white-end data, which means the variance is 1, right? So what this means is that I'm going to be maximizing the expected value of minus log p of v times minus the expected value of minus log p of x. Or I can flip it around. I'm maximizing the difference between the expected value of log of p of x and the end log of p of v, right? And so we're just going to try to maximize this difference. And there's some techniques over here, which I'm not going to have time to go over. But basically, you come up with different functions which can approximate this guy. And each of us, there are all these different functions which approximate this guy. And you can optimize these different functions. And they give us very nice closed form algorithms for performing independent component analysis. So I'll skip some of the other crazy stuff. Let's see. I'm going to have to share this again. I have a couple of minutes, so I'm going to have gone a couple of minutes over, but let me share sound. And let's see how this works.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And here is another one, mixture.
1, 2, 3, 4.
So these are both two mixtures, right, of the same two signals. And here's what independent component analysis will do. If I can find my mouse.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So can you tell me why this is not perfect? Over here. Anybody? Why is this not perfect?
Is it because we're only approximating the independence?
You're only approximating independence. You're coming close, but you're not approximating independence. So now let's see how this really looks, right? So here were my two original signals. So at any time, if I pick one sample from here and one sample from here, that's a two-dimensional point, correct? So if I look at the scatter of these data, this is what the distribution looks like. And you can see roughly that the distribution along X is kind of independent of the distribution along Y. But then when I mix them up, the new scatter becomes something like this. And you can see that the independence is kind of gone. And then when I perform ICA, the scatter goes back to this, which looks much like this guy. And so you're basically recovering the original scatter. What I mean by the things being independent is that if you normalize the distribution along any row, the normalized distributions are all going to be the same. Similarly, the normalized distributions along all columns are going to be the same. But that's not the case here. So ICA will restore the scatter, right? So there's one issue with ICA. If I flip the signs, if I just invert the signal, you're not going to know. You're only looking for statistical independence. So if I scale one of the signal by some factor, you're not going to know. Also, ICA, unlike PCA, doesn't have a notion of importance. It gives you the separate sources, but it doesn't tell you this source is more important than this guy, whereas PCA did. It said this source has more variance than this guy, right? So ICA has all of those restrictions, but then now let's go back to our music again. Here's a piece of music. I'm going to try to decompose it as notes times as the product of notes and a source. And I'm going to try to make the source, rows of the source, statistically independent. So here's the music. And if I run ICA, it actually pulls out the three instruments in this particular example. And so, they sort of end up, the bases in ICA end up representing the building blocks. Now, and so it's very successfully used to generate BCs. And now PCA, we saw PCA could also pull out basic, structures and could be used to represent data. That's what we saw several classes ago. Can we use ICA for this? It turns out, let me see. I should have a picture here. This is what we got with PCA. This is what we got. We got eigenfaces, right? An original face and lots of ghost faces. If I use ICA to find the bases, basically if I decompose my collection of faces to basis times a score, basis times a weight, where the rows of the weight are independent, then your bases all also independent begin looking like faces. So ICA faces actually look like real faces, and you can see that it actually kind of pulls out different kinds of faces. Similarly, if I try to apply it for audio, the bases ICA pulls out begin looking like wavelets. So statistically, what does ICA do? If these were my data, PCA is going to pull out the directions of maximum scatter. It would pull out the two red axes as my bases. ICA will actually pull out the individual sources as shown by these green lines. So ICA finds directions that are statistically independent, and it's going to align with the data. So it's very commonly used in many kinds of signal processing algorithms, especially for EEG signals, where if you're capturing EEG signals, it gets corrupted by the movement of blood, heartbeats, and such like, and ICA can separate them out. But unfortunately, if you go back to our problem, here are the bases that comes out of it. Right, this was PCA, sorry, this is ICA. So it does a slightly better job than PCA of pulling out the individual notes. But not very much. And so ICA has this problem that it gets statistically independent directions. It doesn't have a notion of a best direction. It doesn't have a sense of scaling. And, when there's structure beyond independence in the data, ICA is going to fail. But for data such as these, you can see that it actually does a very beautiful job. Anyway, I'll stop right here. I went way over. I apologize for the extra time taken. And I can wait for a few questions. Otherwise, we'll stop the lecture. Any questions?
Oh, the last sentence that you mentioned, what other structures are there that give meaning to the data apart from independence? If you have two signals that are merging together.
Non-negativity, for example, right? That gave it meaning, correct? Compositionality.
Okay, non-negative as in like signals cannot be
So we
negative.
saw that in the case of that notes will always add compositionally. That's what we used in
Correct.
NMN, remember?
Yes, correct.
Correct.
Okay.
So you have other kinds of constructive, other kind of characteristics that data could have that ICA will not capture.
Yeah.
Right. All right, guys, thank you for your patience, for waiting the extra time. And I apologize for the mess with the mouse, which made the initial portion of the lecture very confused. I'll clean up the slides and post them, okay? Thank you.